Now that we know how to find the critical chi-square values, we're going to use that knowledge in order to construct confidence intervals for either the population variance or the population standard deviation. Now, look at the two formulas for just a second, because they look more complicated than they really are. All of them have the same numerator. These two on the top are for variance. They have two different chi-square values because, of course, the chi-square distribution is not symmetric, so you have to find two separate values. And the only difference between that one for the variance and this one for the standard deviation is that you take the square root of them, because, of course, the standard deviation is the square root of the variance. All right, so if that's the case, you have to have two conditions met. You have to have a simple random sample of size n. And you have to have data come from a population that is normally distributed. Now notice what isn't in here. We don't have the whole, it could be greater than 30, or n times p times 1 minus p is greater than 10. That's not an option anymore. This distribution is so finicky that it has to be that the data is normally distributed. That's it. There is no other option. Normal distribution. And of course, as always, a simple random sample. Those two chi-square values are the critical values, which we just learned how to find on the last video. And the distribution, remember, is not symmetric. So you're not going to construct your intervals the way we did before. Let me pull up the inferential statistics sheet for a second. All right, hold on, let me find it. Here it is. Okay, so the inferential statistics info sheet. If you look at all the other confidence intervals, see the plus or minus right in here, the plus or minus in this one, the plus or minus in this one, and this one. You don't even know how to find these, but you see the plus or minus. But all of these other confidence intervals are built off of the z distribution, like in this one, or the t distribution. But both of those distributions are symmetric around the center of 0. The chi-square distribution is not symmetric, so these two don't have that option of plus or minus. It doesn't work like that the way it does for those other ones. Also remember that the TI calculator does not find these values. You're going to have to do them by hand using the table. All right, so let's look here. Do this on an example. We have the GRE exam, which is a test required for admission to many U.S. graduate schools if you want to get a master's degree or a PhD. The Educational Testing Service, which is ETS, that's the company that produces the test, claims that students' scores on the verbal reasoning portion of the GRE have a mean of 469 and a standard deviation of 120. Suppose a simple random sample of 10 students took their test and their scores are below. So here they are. We can verify that these data are from a normally distributed population. Why is this necessary? Well, you can't make a confidence interval for the population variance or standard deviation unless you know that that data is normal or are normal. So let me go type that up. There we go. In order to make a confidence interval for either sigma or sigma squared, we must know that this distribution is normal. This graph over here on the left, being a normal probability plot, shows the data are normal because no points are outside the boundaries. And by the way, those boundaries, now you can know what they are. See the 95% CI? They're a confidence interval. They're kind of an elaborate confidence interval that's more advanced than our course, but that's what they are. All right, now determine the sample standard deviation. Now, a couple people sometimes forget the symbol for sample standard deviation. You've known it for a while. It's S, right? So what you're looking for is S, sample standard deviation. Now, I was really kind and gave it to you right here in the box, but if I didn't give it to you, you still need to know how to find it. So you go to Stat, you go to Edit, you clear out your old data, and you type in your new data. So it was 489 and so on. Right? All right, once you have those typed in, you go to Stat, Calculate, One Variable Statistics, L1, and then go down to Calculate and press Enter. And you can see S is 105.446 right there. That's your SX. So I'm going to write that down here. S is approximately 105.446. Fabulous. Now what about the variance? Well, the variance is S squared, right? So I'm going to take this value I have and I want to square it. So that would be 105.446 squared. Now you can do this a couple ways. One, you could Let me grab the calculator. So I could type 105.446 and I could square it, enter, and I get about 11118.85892. Or I could use the variables button. It's been a while since we've used it. Variables, VARS, number 5 for statistics, number 3 for SX, and I square it. And that's a little bit more accurate because it actually keeps all the decimal places that way. So 1118.9. So let's see, equals 1118.9. No, there's too many. 11118.9. So it's 11,118.9. Okay, so whether you round it or not, it should be about that much. There's your S squared value. That's your variance, your sample variance. Now we want to construct a confidence interval for the variance. So let me go grab the formula, because as with most things, we are going to have to formula substitution answer. Okay. All right, let me go grab the formula. I'll be right back. All right, there we have it from up above. So it's n minus 1 s squared over that chi-squared alpha over 2, and then chi-squared 1 minus alpha over 2. And then let me start substituting in some numbers. I know that n was 10. So it's 10 minus 1, 10 minus 1. Then I know s squared was the 105.446 squared. Or if you like, you can put in the 111 number. That's fine. I'm just showing the work. Okay. All right, so then we'll need to figure out our chi-square values. So let's go over here. We have a 95, so work on the side. Okay. You know you have a 95% confidence level. So C level equals 95%. That means that alpha is 0.05. Okay, so that means that alpha over 2 is 0.025. Double check that. 0.05, right? So 0.05 over 2 would be 0.025. And that means that 1 minus alpha over 2 would be 0.975. The two of them have to add up to 1. So those two are your columns. Okay? And then you're going to need to go figure out your rows. Well, your row is your degrees of freedom. So degrees of freedom is 10 take away 1, which is 9. That would be your degrees of freedom. That's your row in your table. So now you go to your table and you're going to find your two values. Let me grab the table. That was that wrong table. There it is. So I want 0.025 and 0.975, and I want the row to be 10 minus 1, which is 9. So 0.025 is 19.023 over here, and then 2.7 over here. Okay, so which one's which? Oop, wrong thing. There we go. All right, there we have it. So let me show it to you. Chi squared alpha over 2. Alpha over 2, we just said, is 0.025. It's right here. 0.025. So I want 0.025, 9 is my row. So again, from the table, 0.025, 9 row, that's 19.023. So that's what I write right here. Then I need it again, but for 1 minus alpha over 2. So 1 minus alpha over 2 would be 0.975. And that would be, again, still the 9th row, and that's the 2.700 from the table. Again, 0.975, 9 row, that's 2.700. So those are the numbers you're going to put in. Now the alpha over 2 one is the 0.025. So over on the left, you're going to put in 19.023. And then over on the right-hand one, you want 1 minus. That's the 0.975 number, which is 2.700. So what you need to do is you need to grab your calculator and find each of those numbers. So let me pull up the calculator. All right, so again, I want parentheses, 10 take away 1, close parentheses. Then I wanted 105.446 squared. So you can either type 105.446 and square it, then divide it by 19.023. That'll work. Or you could do 10 take away 1 times 11118.9 because we already found what s squared was. It's right above. And then divide that by 19.023. And you can see they're a tiny bit different from each other, but not in any appreciable way. So I'd say 5260.5 or 0.4647. Technically, the bottom number is the more correct number because it used all the decimal places. So that's what I'll use, 5260.48. Okay, and now the high number, let me grab the calculator again. So I take 10, take away 1, and multiply it by 11118.9. Then I divide it by 2.7, and I get 37063. There we have it. All right, now, what about finding the confidence interval for the population standard deviation? Well, remember that the standard deviation is the square root of the variance, right? So if I have this result, so for variance, the interval was this. Okay. Then the standard deviation will be the square root of that. So for variance, which by the way was sigma squared, that's the interval. So for variance, it was that. For standard deviation, sigma, you'll take the square root of the variance. So take the square root of the interval above. So that means that you're going to take the square root of each of these numbers. So you'll take the square root of this number and the square root of this number, which means our interval is, and I will find this with my calculator. So I want the square root 5260.47942. Then I want the square root of 37063. I get 72.529 and 192.518. There. And you're done. Now, what does this mean? We are 95% confident that the true population proportion of all GRE verbal scores is in between those two numbers. So let me type